What I would like to talk about now are some complications that arise with using this new method of quantum mechanics that we've developed of basis states and operators and so forth. So these are just a few things that would be different than if we were doing things in the more deterministic fashion of classical mechanics. So the first one is the fact that we said in one of the postulates the variables that we're going to be measuring are operators. So variables become operators, which isn't that bad. I mean, this is actually a very elegant way of solving problems in quantum mechanics, except for the fact that we have to worry about commutation. Do these operators now commute? And so one example would be something like position and momentum, which are two variables that came up when we were looking at classical mechanics and trying to solve things with the Hamiltonian or Lagrangian formalism. So if I was to look at something like the product of position and momentum in classical mechanics, if I was to write down that product of position and momentum in quantum mechanics, they would be operators. Okay. However, I've shown previously that they don't commute. And so the question what happens is, what happens if we look at the product of the momentum and the position in this fashion? This isn't necessarily the same thing as looking at the position and momentum here. Whereas in classical mechanics, it doesn't matter if I look at momentum second and position first, or I look at position and then momentum. Those things do commute in classical mechanics. But in quantum mechanics, the operators of position and momentum do not commute. So then the question is, well, what do we do? One way out of this is to consider both of them. Basically consider the symmetry of the situation and say, let's create an operator now which is both the position and the momentum, or the momentum and then the position. And since I'm now operating with both of them, basically operating twice, I'm double counting. And so I just divide by a factor of 2. So this is kind of a trick to get out of the fact that I don't know, what happens if I operate with position first and then momentum, or momentum first and then position. And so we can do tricks like this to kind of hedge our bets and consider both cases of that. Another complication is the fact that we can have degenerate states. So what do we do with degenerate states? Basically meaning that if I have some eigenvalue omega, which is the same thing as omega 1 and omega 2. So if I'm considering a problem, an eigenvalue problem, where I have two solutions, omega 1 and omega 2, but in this case, omega 1 is equal to omega 2, then how do I consider the that measurement? Because I should measure it twice. Or basically, another way of saying is that I measure the answer to be omega, but I can get to it from two different ways, either through omega 1 and omega 2. And so one thing to consider is that when we're calculating the probability is that we consider both of them. So I can write the two degenerate states as the eigenvalue is omega, but this is the first, or omega comma 2. So these are my two degenerate states, which gives me the same result, but it's two possibilities that give me the same result. So if I'm calculating the probability that I'm going to get the value omega, I have to consider both cases. Or basically it's a superposition of those two states. Like so. So I get the probability of being in state 1, giving me a value of omega, or being in state 2. Let me fix this. Or being in state 2. So I have both of those. So basically it's the sum of those probabilities. The sum of getting the same answer, but getting it from either from state 1 or from state 2. So I could arrive at this with my projection operator. Where now this is that fancy P. So projecting to get the answer omega would just be omega from state 1 plus omega from state 2 like so. So in the end, my probability to be in this state omega, or to get the answer, the eigenvalue of omega, would just be applying the projection operator to my general basis psi. Okay. Another complication that we have to worry about is the fact that what we're going to deal with are not discrete states, but continuous states. So another way of saying is that this eigenvalue problem is continuous. So in that case, if I have a state psi, it is the sum or the integral over the projection of all possible states, omega, on psi, and then I integrate over the variable omega. In this case, what we've now defined is something called the wave function. Or sometimes called the amplitude. So the wave function is this mysterious mathematical function which Born said is once we have the wave function, if we square it with a complex conjugate, then that square of the wave function gives us the probability density in order to compare with measurement, to come up with a result, a prediction of what's going to happen in this particular experiment. So here's my wave function, then my probability density is the norm, or which I could write out as this right here, which ends up being psi star psi. So this is the connection that we have with the other way of talking about quantum mechanics, more of the Schrodinger approach to quantum mechanics. The Schrodinger approach is to have the square of the wave functions, so the psi star psi, and we solve for the wave functions with Schrodinger's equation. The Heisenberg-Dirac approach approaches it from basis states where the basis, you're projecting the basis of omega onto psi in order to extract the wave function. So the total probability is the integral, the probability density, over whatever variable it is, whether it be space or momentum. So I can write this out now as the integral of omega projected onto psi squared, which is the integral of what I just wrote above, which is the integral of psi star psi, which is, in this case, 1. Because when we sum up all the possibilities, sum up all the probabilities of a certain reaction, it should sum up to 1. So all those different results should have their individual probabilities, and when you sum them all up, you get a probability of 1. So the final complication with quantum mechanics is that there are going to be certain operators like intrinsic spin which do not have classical analogs. So, I mean, so far we've always talked about variables that do have a classical analog. We talk about position. We can try and measure the position from the wave functions. We can measure the momentum. We can measure the energy. All of these operators have some, we can do that. We can measure those quantities in classical mechanics as well as quantum mechanics. But we're going to find out later on that there are certain things that do not have classical variables, but there are quantum mechanical operators to measure them. Spin is one of them, but I don't want to get into what spin is yet. But basically things like, spin is the origin of the magnetic field from the electrons in the nucleus and the atom. And there are other things too, which do not have classical analogs, like isospin and other things related to, like, the weak interaction. But anyway, so we're not really going to get into that. But just to say that, when we do, we'll try and grapple with the fact that quantum mechanics can study certain things, but classical mechanics just cannot. There is no classical example of this type of operator.